Hi everyone, welcome to our talk on MENYO-20k. It's a new multi-domain English to Yoruba machine translation corpora. And this was done in a collaboration with Dana, Jesujoba, Damilola, Adeshina, Mofe, Ayodele, and Christina for the Africa NLP workshop. And so in large-scale machine translation models, often trained on hundreds of languages, the evaluation is mostly done on high-resource languages. And one of the reasons is because there are no standardized evaluation corpora for the low-resource languages. There have been efforts to create this for other languages, and we also created for Yoruba to English machine translation. So our major contribution is to create MENYO-20k, which is the first multi-domain parallel corpus. We also provide several neural machine translation benchmarks on this dataset, achieving the state of the art, especially from English to Yoruba. We analyze the MT performance on different domains. The Yoruba language is native to Nigeria and the Republic of Benin, but widely spoken across West Africa, as you can see in the map on the right-hand side. It's the third most spoken language in Africa after Swahili and Hausa. It makes use of the Latin script. It is tonal, and the tones are also represented in the text, including the underdots, which are special characters used in the Yoruba language. So we refer to all this as diacritics. So our pipeline is the following. We first do the normalization form C, Unicode, and after that, so that all the text that we gathered can be in the same format. And also, most importantly, so that the diacritics can stay properly on the text. So after that, we did punctuation normalization, followed by tokenization, and true casing, and the last, of course, we did BPE with 40k merge operations. From our initial experiment, we found out that the one with larger vocabulary is better. Our final data set is this, MENYO-20k, which is from different corpora. We have the news domain, and we have close to 10,000 sentences for there, where we have around 5,000 in the training and 3,000 in the test set. We also have other domains like TED Talks, where most of it, the data set is used for evaluation. We also have the book, corpus, the digital, which are more technical terms that are very difficult to translate. We have proverbs, which are more of information from elderly people, and other domain. Our baseline model, the Bible, around 30,000 sentences, and JW around 460,000. In total, we have around 500,000 sentences. This is what we use for the experiment. And after this, I will hand over to my colleague, Dana. Thank you.
All right, let me now tell you a bit about our domain analysis experiments. We perform these by looking at two different metrics, the perplexity of a language model and the vocabulary coverage. On this slide, you see the perplexity of a 5-gram language model trained on 3 different training subsets. So in the first row, you can see the perplexity of the language model trained on the JW300 corpus. In the second row, you can see the perplexity of a language model trained on the JW300 and the Bible corpus. And in the last row, you can see the perplexity of a language model trained on the JW300 corpus, the Bible corpus, and the MENYO-20k corpus. And then we test these different language models on the different test sets or test subdomains, namely the news domain, the TED domain, the books domain, the proverbs domain, and the digital domain. On the left side, you can see the perplexities of the English data, and on the right side, you can see the perplexity of the Yoruba data. And basically what we can see is that the perplexity when using small amounts of data, such as the JW300 corpus and the Bible corpus, well, the perplexity is quite high, especially for domains such as news and digital. This is the case for both English and Yoruba. But once we add the MENYO-20k corpus, which covers a bunch of different domains, the perplexity drops quite drastically, especially for domains such as news and digital, but also for all other domains. And by the way, if you're wondering why JW300 and Bible are actually quite okay on the TED domain, it might be because they are quite close to the TED domain in the sense that the TED domain and the Bible and JW corpora all contain a lot of speech and monologues. So this is why the perplexity might be especially low on the TED domain when using JW300 and Bible only. In any case, adding the MENYO-20k corpus did improve the perplexity across all domains. Now what we can also look at is the vocabulary coverage of the training data, of the test data based on the training data. And on the left side, you can see the English corpus, and on the right side, you can see the vocabulary coverage on the Yoruba corpora. And basically what we can see is that for English, the vocabulary coverage is actually pretty good across almost all domains except news. But by adding the MENYO-20k data to the training data, actually the vocabulary coverage goes up by 4%, so that's quite nice. And we get a generally pretty good vocabulary coverage. For Yoruba, this is a bit more difficult. We can see that the vocabulary coverage of the different test domains is a lot lower. It's still quite okay for the books domain and the proverbs domain. But in any case, once we add the MENYO-20k data, this also goes up across all domains, and we reach vocabulary coverage of up to 82.2 on the proverbs domain. The news domain still seems to be quite difficult, probably due to the formal language and technical vocabulary used in news text. So there we get a vocabulary coverage of 60.9. Anyway, still better than 40.0. So all in all, we can say that the domain coverage goes up. So we get a better vocabulary coverage, and we also get lower perplexities when adding the MENYO-20k corpus across all domains. And now our colleague Jesse Joba will talk a bit about our NMT experiments and our results there.
Okay, now I will present our experiments and our results. We trained our models using the transformer-based model architecture with standard parameters, using the 3 different data sets as used in the domain analysis experiments, which were Bible, JW300, and MENYO-20k corpora. On different subsets of the training data, we trained 4 basic NMT systems, while we also trained a transfer model by fine-tuning the best checkpoint obtained from training on the combination of the JW300 and the Bible corpora on MENYO-20k, therefore resulting in 5 different NMT models in total for each translation direction. The resulting models were evaluated using the tokenized BLUE score. Now to the results. Looking at the top section of the table, BLUE scores obtained after training on the Bible is small due to the size of the Bible corpus, which contains approximately 30,000 parallel sentences. Training on a larger corpus, that is the JW300, leads to higher BLUE score of 7.46 in the English to Yoruba direction and 9.59 in the Yoruba to English direction. We observed that fine-tuning worked better for English to Yoruba direction than a model trained on the combination of all the data sets, and it was less effective for the Yoruba to English direction. Furthermore, we compared 3 external NMT systems, which are Opus MT, M2M100, and Google MNMT. Opus MT, which was trained on the JW300 corpus and other corpora on the Opus website, has no English to Yoruba model. However, it achieved a 5.87 BLUE score in the Yoruba to English direction. This is largely outperformed by our simple model trained on just JW300. Similarly, the Facebook's M2M100 was largely outperformed by our simple model. A manual examination conducted over the laser extractions used for this model showed that they are noisy. On the other hand, the Google model obtained an impressive result in the Yoruba to English direction, while in the opposite direction, a significantly lower translation performance was observed. This is because the diacritics were lost in the Google translation engine. In a previous work, we found out that diacritics are important for Yoruba embedding. As a result, we decided to verify if diacritics can help to disambiguate translation for Yoruba. We trained models from Yoruba to English direction without diacritics, ignoring the other direction because one cannot generate correct Yoruba text without diacritics. From our results, we observed that when the training data is far from the text domain, as seen in JW300 and its combination with the Bible, adding diacritics can help. However, when more data is present or the test data are in the same domain as the training data, diacritics becomes less important. Lastly, we evaluated each model on the different domain subsets of the test data. The results are in line with the language model perplexity results and the conclusion drawn in the domain analysis section as presented by Dana. From our results, we discovered that proverb domain was especially difficult in both directions as it obtained the lowest translation performance across all the domains. TED Talk is the best performing test domain because of the decent base coverage of the test domain of the TED domain by JW300 and the Bible, which are both monologues. Digital domain benefited from the MENYO owing to the introduction of the domain content in the MENYO data. In conclusion, we present MENYO-20k corpus, English to Yoruba multi-domain parallel corpus, and then we provide several NMT benchmarks for future research on the English to Yoruba machine translation task. We analyzed the domain differences on the MENYO-20k corpus, and we found out that fine-tuning on the 10k parallel sentences from MENYO-20k improves the translation performance over all domains. And the combination of all the corpora outperforms popular pre-trained machine translation models, especially in the English to Yoruba direction. Thank you for listening.